I want to introduce you to a mathematical tool, an extremely powerful mathematical tool that you've probably never used before, probably never seen before. Or if you have seen it and used it a little bit, maybe I can help you learn how to understand it a little more deeply. So the context here is that as people developed calculus, they started coming upon more and more complex functions that they wanted to integrate. Or maybe it wasn't just for integration, maybe it was other types of equations that involved integration. But as you look at more complex physical situations and problems to solve, you'll come across more complicated families of functions that you would like to find antiderivatives for. And there's a lot of functions that you just don't know how to find antiderivatives for directly. For example, something as simple as e to the x squared. If you're a Calculus 1 student or a lower Calculus 2 student, maybe any Calculus 2 student, you probably wouldn't be able to find this. You could try using a u substitution, but if u is x squared, then du would have an x in it. There's no x here. You could try different techniques. Most likely you would not be able to come up with it. But we would like to be able to find these if possible. So what I'm going to give you is a tool that, it's really an ingenious tool that people developed that allows you to get approximations in a very precise way, where you can get actually to any level of precision that you want in a nice straightforward way. So here is the setup. If I have a function like, let's say, e to the x, I want to approximate it with the most simple functions that I know. The most simple function that I can possibly think of to approximate this function is a constant function. And I'm going to approximate near x equals 0. So if I'm going to use a constant function, and I know that my function is equal to 1 at x equals 0, then the constant function that I'm looking for that can approximate my function values fairly decently around x equals 0 would be the function y equals 1. I'm going to call it p0 of x. Now, the next most simple type of function that I'm going to look for is I'm going to allow a power of x. So I'm going to allow this to be a general linear function. And if you've taken Calculus 1, if you've worked with derivatives, then you probably already know how to do this. If you want to get a function that approximates e to the x, you could grab the tangent line at that point x equals 0. Then this red line approximates the function better than the purple line. And even as you go further out, it approximates it a little better. But it's still a bad approximation if you go far enough out. If you remember the way that you actually get this function, this red line is you have the y-intercept, which is 1, and then you need the slope. And the slope of the tangent line is the derivative of the function. So if I'm allowing 1 power of x, I'm using p for polynomial. This is a 0th degree polynomial and a 1st degree polynomial. Constant is 1. And then I'm just going to have the slope of this line times x. Slope is the derivative evaluated at 0. The derivative is e to the x. So I plug in x equals 0, I get 1. That's the slope. So 1 times x. That's the tangent line. Now what I would like to do is go up 1 more degree. So I want p2. And I'm going to keep the 1 plus x. And then I'm I'm going to have a coefficient in front of x squared, and I don't know what that coefficient is yet. So the idea is that if I allow one more power of x, I'll have a function that approximates e to the x better for a longer range, or at least for some little area around x equals 0. You could keep this up. You could keep going to a cubic function. You could get fourth degree, fifth degree, and so on, and you'll get better and better approximations to the function y equals e to the x. So you could keep going like this. You could go all the way down to the nth power. So you'd have something like 1 plus x plus some coefficient type. Well, I'm going to use a letter. I'm going to call them c's, these coefficients. So I'll call this c2 x squared plus c3 x cubed, and so on, all the way to the nth power. So cn x to the n. You get better and better approximations for this function, and it turns out if you use the limit just like you did with derivatives, like you did with integrals, then when you take the limit of this process as n goes to infinity, so limit as n goes to infinity, you can get an expression for e to the x. You get exactly e to the x. So if you just keep going with this, and you just keep going forever, it's like an infinite polynomial that gives you exactly e to the x. If you want to know how to find these constants, I will do this for you. You have to learn about infinite series. One advantage of this is that if I want to solve the integral of e to the x squared, for example, or at least get really good approximations with applications that involve this, then I'll get this kind of expression for it, and then I'll plug in whatever x values I need, and then I'll go as far as I want to whatever level of precision that I need, and then I'll cut off the rest of it. And so you can balance out the time it takes to make the calculation with how much precision you need. So there's sort of a cost and an efficiency here that you have to balance out in applications. But it's an extremely powerful tool. It turns out that you can do this for any function. So it doesn't have to be e to the x. You can go through this process for any function. So for any function f of x, you can do something like constant term plus c1x plus c2x squared, and keep going. You can represent your function like that. There's a nice pattern for how this shows up. I'm not going to give that to you now. You have to study that later. Even though you can do this for any function, the thing is that it doesn't work for all values of x all the time. Sometimes it does work for all values of x for some functions, and then for other functions, it only works for certain values of x. But there are nice ways of saying exactly what values of x it does work for, and they come in nicely organized sets of numbers. But as you go deeper into this and you want to use this more, it becomes more and more important to be able to say when this gives you something meaningful and then when it diverges. So for example, if I were to plug in x equals 2 into this, then maybe I would be right here on the graph. If I'm really going to get a good approximation for that y value, which is e squared, then this needs to be something that is not running off to infinity, basically. So I could plug in 2 into here, and once I know what those coefficients are, there are ways to test this based on the pattern of those coefficients to see whether this series converges, whether this this infinite sum, which we'll call an infinite series, whether it converges to something finite or whether it's infinite. You will spend a lot of time when you study this type of series, this type of infinite sum, trying to figure out when things do converge to something finite and when they diverge. Because people were able to use this to solve really nice physical applications that they had never been able to solve before, like Newton and people after him. But there was also just ridiculous stuff that was coming out that didn't make any sense when people were manipulating these and like adding and subtracting and multiplying and dividing. So it took people a long time to be able to say exactly what's happening and to develop a nice formalism for it. But you can start using these before you develop all the formalism. Before you develop all the formalism.